The cosmos now harbors a groundbreaking instrument launched into orbit, the James Webb Space Telescope. This technological marvel works like a powerful magnifying glass, offering unprecedented clarity in revealing the intricate details of distant planets. Recently, the JWST set its sights on a remarkable target, K2-18b, an enigmatic exoplanet. Initial observations of K2-18b sparked a wave of excitement within the scientific community. This celestial body was no ordinary planet. Not only did K2-18b exhibit the presence of water vapor, a potential indicator of availability, but it also contained a molecule that aroused deep intrigue, a compound often associated with biological processes on Earth. Could this be the momentous revelation humanity was waiting for, the confirmation of extraterrestrial life? In this video, we'll dwell deeper into K2-18b, exploring the scientific challenges and far-reaching implications that could reshape our understanding of the universe. Let's embark on an investigation of the first tangible image of K2-18b. Located 120 light-years away, K2-18b is a super-Earth within its solar system. Distinguished by its classification as a sub-Neptune, unlike anything in our own cosmic backyard, this planet is larger than Earth but smaller than Neptune, defying conventional planetary categories. This unique status presents a considerable challenge for scientists trying to unravel the mysteries of K2-18b. While rocky planets like Earth and Mars serve as benchmarks for hypothesis building, and distant gas giants like Jupiter and Saturn offer tentative comparisons for understanding this distant world, sub-Neptunes, planets with no familiar counterparts in our solar system, remain enigmas. The data available so far suggests some fascinating theories. For example, K2-18b orbits in the habitable zone of its host star, a red dwarf called K2-18, raising the possibility that its surface may harbor liquid water, similar to Earth's oceans. It is crucial to note that K2-18b's orbit around its host star is much closer than Earth's orbit around the Sun. While 1 astronomical unit, AU, represents the average distance between Earth and the Sun, K2-18b is only 18 cents from its star, even closer than Mercury. This proximity means that a year on K2-18b lasts only 13 Earth days. Fortunately, K2-18b's host star, K2-18, is a red dwarf, which emits less heat than our Sun. This prevents K2-18b's surface from being completely scorched, unlike what would happen under a hotter, more luminous star. In fact, K2-18b's lower stellar luminosity has turned out to be a major benefit as it has allowed signs of vaporized water to be detected in its atmosphere, a groundbreaking discovery suggesting the presence of biological signatures similar to those we find on Earth. This discovery, which furthers the scientific interest in this exoplanet, is truly revolutionary. The fact that methane decomposes rapidly under solar radiation added even more excitement. The JWST also detected carbon dioxide, a more common atmospheric component. However, the combined discovery of methane and CO was exceptional. Even more intriguing, the telescope identified traces of dimethyl sulfide, DMS. Unlike methane, DMS is not commonly found in Earth's natural environment. Instead, it is a molecule produced exclusively by biological processes, primarily by microorganisms in the ocean, such as phytoplankton. On Earth, dimethyl sulfide serves as a reliable biomarker. Its detection on K2-18b is particularly intriguing because this planet resides around a red dwarf star known for intense radiation and considered inhospitable to life. Yet, K2-18b defied these expectations. It is crucial that the planet receives a similar level of radiation and resides within its star's habitable zone, where temperatures are neither too hot nor too cold for liquid water to exist, provided there is a stable atmosphere. In such a case, K2-18b could have temperatures comparable to those of Earth. Although its atmosphere is hydrogen-dominated, which may make its ocean slightly warmer, the proximity to its star is just right to prevent complete evaporation of surface water. This detail is of great importance, especially in light of recent research suggesting that surface water could be a distinguishing feature of exoplanets like K2-18b. Stay tuned, because soon we will dive into revealing details about the mystery of these exotic worlds. In 2021, astrophysicist Nicky Madhusudhan, known for his possible discovery of DMS in space, proposed a new category of extrasolar planets in a fascinating paper published in the Astrophysical Journal, Sub-Neptunes Cradled Beneath a Thick Hydrogen-Rich Atmosphere. Madhusudhan chose to call this work Hycean, a name that suggests their watery, mysterious nature. If these so-called water giants exist, they will be radically different from anything we've ever seen before. Though they could be up to 10 times the mass of Earth and twice the radius, they wouldn't behave like a furnace of steam. Yes, They will be incredibly hot, approaching 200 degrees Celsius. But what would define them is an astonishing feature: a colossal layer of water that could represent up to 90% of the planet's mass. This vast ocean could, in theory, harbor the potential ingredients for basic microbial life. Their dense atmospheres trap heat from the star, allowing liquid water to exist over much wider range of distances than on rocky planets like Earth. Sub-Neptunes are relatively common, and Hycean worlds benefit from this extended habitable zone. This makes them ideal targets for the search for life beyond our own planet. Larger planets are easier to detect from far distances, making them prime candidates for telescope-based investigations. Dr. Madhusudhan's research team used the revolutionary James Webb Telescope to observe K2-12B, a possible alien world. This tool could be crucial in our search for extraterrestrial life. But there is a challenge. Even with advanced technology like the James Webb, detecting these Hycean ocean worlds is a difficult task. The key to unlocking the secrets of K2-12B lies in meticulously planned observation blocks requiring a total of 5 hours of observing time, divided into 2 separate observation sessions. K2-12B played a crucial role in a celestial event known as a transit, during which the exoplanet passes directly between Earth and its parent star. During the transit, James Webb captured starlight passing through K2-12B's atmosphere. The beauty of this technique lies in the unique fingerprint that starlight carries, a universal language revealing the elemental and molecular composition of the material it interacts with. By dispersing the light into its component wavelengths, just like a prism breaks white light into a spectrum, scientists can analyze these fingerprints to identify atmospheric molecules. If certain wavelengths are missing from the observed spectrum, that provides important clues about specific gases present, or absent, in the planet's atmosphere. This spectroscopic transit method has become the cornerstone of modern exoplanet atmospheric studies. From that initial dataset, researchers identified distinct absorption features corresponding to water vapor, methane, carbon dioxide, and the particularly rare presence of dimethyl sulfide. The detection of all these molecules combined, especially DMS, marks a pivotal moment in exoplanet research. For decades, methane and carbon dioxide have been considered potential biosignatures. Discovering them is exciting, but often ambiguous because they can arise from non-biological sources. Dimethyl sulfide, however, is widely considered a more reliable indicator of biological activity, at least in Earth-like conditions, since the known production of DMS is almost entirely biological. With these molecules detected around a water-rich planet inside the habitable zone of a red dwarf star, the possibility of Hycean life moves from intriguing theory to empirical investigation. However, skepticism and caution remain. While K2-12B's signals are unprecedentedly suggestive, alternative abiotic mechanisms could still explain some of the observed spectra. For example, interactions between stellar radiation and surface minerals, volcanic processes, or photochemical reactions could mimic certain biomarker signals. The pressure, temperature, and composition of a hydrogen-rich atmosphere, unlike Earth's nitrogen-oxygen mix, also complicate interpretations. Understanding these complexities will require follow-up observations. Additional transits observed in alternative wavelengths, particularly mid-infrared, will help distinguish between competing biochemical and abiotic explanations. Complementary observations from other future telescopes, such as the Extremely Large Telescope, ELT, or space missions like HabEx or LUVOIR, could enable direct imaging, surface mapping, or even detection of seasonal variations. These future instruments will be essential for validating whether K2-12B truly is a living world or a false positive with Earth-like signatures forged by geology. By documenting in exquisite detail the atmosphere of a transiting sub-Neptune, the James Webb Space Telescope moves us one step further along a path leading to potential disease-changing revelations. K2-12B's study marks a pivot from mere cataloging of exoplanets to characterizing their habitability in depth, and even seeking signs of life. As we continue to observe, analyze, confirm, and refine, we inch toward what may become the greatest discovery in human history: evidence that life, even in simple microbial form, exists beyond our planet. In conclusion, K2-12B and other Hycean worlds broaden our concept of habitable planets. By embracing planets unlike anything in the solar system, water worlds, hydrogen-rich Neptunes, sub-Neptunes, we become more